So this is a derivative question that's coming from practice problems for the at the very end of the exponent and logarithmic derivative rules. And these two questions that we're going to do is actually kind of a mini review. It's going to do the derivative rules for both constants and the polynomials, as well as having the rules for exponentials and logarithms, just so that you get some layered learning, so you're not memorizing a set of rules and then moving on to the next set of rules, and then there's no connect or review. So it's very, very easy to forget a rule if you don't continue to use it. So that's why all these rules are combined in this particular lesson. But the way we do this is we first note that whenever you have a long kind of chain of expressions or functions put together, the first thing to note is that these are all combined through addition. And we know that through derivative properties, that whenever you add functions together and then you take the derivative, you could also just take the derivatives of each individual function separately. So written out, you're really only taking one derivative rule at a time. So the first function is is k, and then through the additive property, I can add then the next derivative, so the derivative of x to the n, and then I can continue down the line. So I can separate that big chain function of a bunch of added things together and just split it up so that it's easier to understand. So derivative of e to the x, the derivative of a to the x, the derivative of the natural log of x, and the derivative of the log base a of x. So when you split up all of the derivative rules like this, all you're really doing when you're taking this derivative is remembering what each rule was for each one of these. So the derivative of a constant, that's what this k is, the derivative of any constant is always going to be 0. And that should make intuitive sense in one regard, because a constant function looks like a flat line. And constant, the very word constant, implies no change is happening. And since the derivative is kind of understood to be the definition kind of how we describe and quantify change, well, then something that never changes should experience 0 change. And so that's why the derivative of the constants are just 0. So we have 0 coming from that derivative, and then we can just add these up. So plus, now the derivative of a polynomial term, so the power rule is what we do is we take this exponent and we throw it down as a constant out front, and then we decrease it by 1. So I throw the power down as a constant out front, and then I reduce my power by 1. And that is the power rule. And then that's all there is for that. The derivative of e to the x is a very, very special derivative. This one's pretty easy to memorize because the derivative of e to the x is itself e to the x. The e to the x function is the function family that gives its own rate of change back. It's a very, very quickly growing function. It kind of looks something like that. So, and in general, if you multiply the exponential curve by some constant, so if you have some function that's like a constant c times e to the x, then all of its derivatives are also going to be c e to the x. That's a good one to memorize because it's pretty easy. And so here's a different one. So this is e to the x. That's a specific kind of exponential function. Now here's a to the x, where this is now a general exponential function. So a can now be any constant and not specifically the natural number e. And the way you do this, the way I like to actually remember these rules, I'll talk about this a little bit more after doing this problem, is it's very similar to the natural number version of the function. So since e to the x just gives e to the x, the derivative of a to the x, where a could be a number like 2 or 4 or 7, you start the same way. You just have a to the x, but the modification you have is you tack on this natural log of a and multiply that constant to the a to the x. So you can see that you could actually derive this rule by plugging it into the general rule, because the natural log of e gives just 1. So you would have e to the x times the natural log of e, which is just e to the x times 1, which is e to the x. So memorize these rules kind of together, because they're really, really related. Well, technically speaking, the exponential rule is just an application, a specific example of the general exponent. So yes, that's how that one works. It's a to the x, you replicate the exponential, but then you multiply this little tag, the natural log of a constant. Now, the derivative of the natural log of x is a very, very common and important derivative rule to memorize for AP Calculus and Calculus just in general. And it's 1 over x. That gives you the reciprocal there, or the inverse function. And in a similar way to how this little tag, natural log of a, is going to become important, it also is really helpful when going from the natural version to the general version. Again, this is, actually, let me color code this. So in green, these are the natural versions. So natural number e, so the natural exponential, the natural logarithm. And then in blue here, this is the general forms of those. And so what's going to be the difference is adding this tag, natural log of a, whenever you're talking about the general version. So over here, the derivative of the logarithm base a, it'll start exactly the same as the natural version. So if you memorize the natural version, you start with the natural version. And then you multiply by that variable, the tag natural log of a. So that comes up again, it resurfaces. And then that, in one sense, we can basically just take the 0 off because it's redundant, and there you go, there's your answer. So this would be the solution, the derivative to this. Now, a quick note about memorizing these rules. I like to put them kind of side by side. So e to the x becomes e to the x when you take the derivative. And a to the x becomes a to the x times, that looks like a 9. Let me rewrite that. A to the x times the natural log of a. And then when you compare the logarithms, so the natural log of x, when you take the derivative, becomes 1 over x, that the general log base a of x is going to become 1 over x times the natural log of a. So here's how, kind of how I've continued to keep these memorized, even though I haven't been, taking calculus in a very long time. All I do is I memorize these. I memorize this rule right here, and I memorize this rule right here. And here's why that's all I need to memorize. It's because then if I'm encountered with the general exponential, all I got to do is tack on the natural log of a after replicating the rule. So here, it's a to the x. I just replicate the a to the x, but don't forget to tack on the natural log of a. And then with the general logarithm, I do the 1 over x, and then I simply don't forget to tack on natural log of a there next to the x. So that's a really, really nice little pattern. If you memorize, that's why I clumped those rules together. So if you don't memorize them in that grouping, it can be difficult to use the memory trick. But I'm a firm believer in memory tricks. So take advantage of that. It'll become very, very helpful to keep everything sorted out, especially as you continue to move through more derivative rules. So let's go to the other exercise. And this is a little bit, there's a little bit more going on here, so we can talk about it. Again, notice that we have a bunch of different functions, but they're all combined with addition here. So we're just adding a bunch of functions together. So we can split the derivative up through that additive property, and you're really just taking the derivatives of individual things. So the derivative of the cube root of e plus the derivative of pi squared times x to the pi squared power minus 1. So this entire thing is the exponent there. I'll just keep it in parentheses so it's clear. And then the derivative of 7e to the x plus, and then the very last function here is 2 times the natural log of the square root of x. So we will have a chain rule going on. Now, we have 1, 2, 3, 4 different functions here. So the first function is the cube root of e. Now, it's very, very tempting to see the radical sign and immediately try to think this is a function. But when you really think about it, the number e is a constant. And then if you take a number that's a constant, and then you cube root a constant, well, it's not going to suddenly become like variable to something. It's still just a constant. So ultimately, the value of this constant really doesn't matter because it doesn't change. And since the derivative is only interested in how this is changing with respect to x, we see that it just never does change with respect to x. So its change is 0. It's a constant, so its derivative is just 0. Regardless of how weird or complicated that constant looks, it's just going to be 0. Now, we have a bunch of these constant multiple rules. And so what I'll do is I'll actually write this out so you can see what's going on. Pi squared is a constant. And when you have a derivative, in general, I'll write this over here. So if you're taking the derivative where you have some sort of a constant multiplied by your function, then what you can do is you pull the constant outside of the derivative because it won't have an effect on the derivative of the function. So we're gonna write out this property, that constant multiple property, and see what we get. So we can pull out the pi squared from the derivative, because really what the function is, it's just the x raised to this power of pi squared minus 1 and the exponent here. And then here, 7 is just a constant multiplied by the function e to the x. So we can take that constant multiple out of the derivative. So we have 7 times the derivative of e to the x. And then this last one is that number 2. So we have the constant multiple 2 times the derivative of the natural log of the square root of x. And now that we have that sorted out, we can look at these derivative rules again. So the 0 is gone over here on the left. So we're left with the pi squared on the outside. Now, when we look at what this derivative rule is going to be, it's just a power rule. And the way the power works is whatever that power is, regardless of what it looks like and regardless of what symbols are in there, you're going to just throw it down as a constant in front. So I'm going to take this entire pi squared plus 1, or pi squared minus 1, take that entire power and move it down as a constant in front of the x. And then, again, I just decrease that power by 1. So I have pi squared minus 1, but then I'm decreasing it again. So I have minus 2 by lowering that power by 1. So that's that power rule. Now we have the 7. Now the derivative of e to the x, again, so e to the x is nice. It's just itself when you take the derivative. And then over here, let's take a look at what this chain rule is going to do. So we have the 2 standing outside. Now the natural log of, and then here's the input. So the rule for natural log is simply 1 over whatever's put inside of the function. So we have 1 over the square root of x. So we take this entire thing and we treat it like that's the input. So it's going to go into the denominator. The original rule, don't forget, is just that the derivative of the natural log of x is 1 over x. So you take the argument of the function and you put it in the denominator. So we're doing the same thing over here. It just so happens that the argument of natural log is now the square root of x, and that's okay. So we can stick that in the denominator. Now the only thing we need to accommodate is the chain rule here, because the square root of x is in itself a function. And that's what happens when you put a function and compose it inside of another function. So we just multiply by the derivative times the derivative of the square root of x. And that's the chain rule right there. So here's the derivative rule, and then we multiply by the derivative of that composed function. That right there is the chain rule. So on this next line, we can start to put everything together. So we have pi squared times pi squared minus 1, x to the pi squared minus 2, just copying that over. We still have our 7e to the x, 7e to the x. And then now let's work on simplifying this. So we have the 2 over the square root of x. And then the derivative of the square root of x. It's it's much easier to take these derivative rules when you understand the radical as a fractional exponent. So what we really have here is the derivative of x to the 1/2 power. And now that we've written it as a power of x, we can just use the power rule and it'll be much easier to do. So let's see, I guess I'll write it one more time here. So pi squared minus 1, x, pi squared minus 2, 7e to the x plus 2 over the square root of x. So when we take the power rule, the exponent is 1/2. So I'm going to bring it down. So I bring down the 1/2 out of the power and out front of the x. Now I need to decrease the power by 1. So 1/2, I'm going to subtract 1 from that. And 1/2 minus 1 is negative 1/2. And then all that's left is to just simplify some algebra. So of first things to know is the 2's are going to cancel. And then another thing to note is that we've got 1 over the square root of x times x to the minus 1/2. Now, when you have a negative exponent, then it's the same. You can put that in the denominator and then it'll be positive. So this is really 1 over x to the 1/2. But like we noted, x to the 1/2, that's just another way to say the square root of x. So we're really 1 over the square root of x. And then when you multiply this together, you got the square root of x times the square root of x. Well, that's just x. So we end up with just 1 over x. So all of this simplifies algebraically to 1 over x. So this is how we evaluate that derivative right here.